I want to talk about something called the octet rule. In Chapter 6, we learned that noble gases are unreactive in chemical reactions, and in 1916, Gilbert Lewis used this fact to explain why atoms form certain kinds of ions and molecules. He called it the octet rule, and it said that in forming compounds, atoms tend to achieve a noble gas configuration, which is 8 in the outer level. That's a stable configuration, and atoms tend to behave chemically in ways to become stable. Each noble gas, except for helium, which has 2 electrons, has 8 in the outer shell. So that's why we call it the octet rule. So metals lose electrons to attain this stable noble gas configuration, and it makes them positive ions or cations in the process. So if we look at the electron configuration, it makes sense for a metal to lose electrons. So here's a metal like sodium. 1s2, 2s2, 2p6, 3s1. Now, this is not a complete outer shell, so the S only has 1 electron, and it has none in the p sublevel. It doesn't even have p sublevel. But if we look at the second level, the second shell, it is filled. 2s2, 2p6, that's a completely filled second level. So in a way, it's kind of easier for a sodium atom to lose this 1 electron to become stable and have a complete outer second shell than it would be for this sodium atom to gain 7 electrons. It doesn't have the electronegativity to do that in the first place. So sodium's going to lose that valence electron in the third shell, and it's going to obtain this configuration, 1s2, 2s2, 2p6. This is a noble gas configuration. It has 8 in the outer shell, or a complete octet is another word to say that. So metals will usually have few valence electrons, usually 3 or less. Calcium, for example, only has 2 valence electrons. So if we were writing the electron diagram for calcium, it would be the symbol Ca, and 1, 2 electrons. Now, metals, we say, tend to lose valence electrons in the course of chemical reactions. So it is easier for calcium to lose 2 than to gain 6, and because of its weak pulling power, it doesn't have a lot of protons, it's going to lose these 2 electrons. So these electrons are going to go away and be taken by something that has a much higher electronegativity. And there they go. In the process of doing this, it's going to obtain a charge. It was neutral as a calcium atom, but now as a positive ion, it is a 2+ charge. And it's no longer a calcium atom at this point. We need to rename it. So to name an ion of a metal, it's really easy. All you need to do is write the word ion after the name. So a calcium atom loses 2 electrons and becomes a calcium ion. And you may say, well, this is an electron dot diagram. Where are the dots? And there are none. That's the thing with metals. Metals have no dots in an electron dot diagram, but you have to show the charge or it's incorrect, or else it wouldn't be an ion. So why does it get a 2+ charge? Let's look at the math here. So the atom of calcium had 20 protons because it's element 20 on the table. The number of protons also equal the number of electrons. So 20 positive charges are balanced out by 20 negative charges to give an overall charge of 0 or neutral. When it becomes an ion, it still has those 20 protons. We didn't move any protons out of the nucleus, but we lost those 2 electrons in its valence shell. So now we're down to 18 negative electrons. So now the positives outweigh the negatives by 2, which is why we have a 2+ charge on that ion. So let's do scandium 21. This is a special situation. Here's the electron configuration. It is in the transition metals, and you can see that because we have electrons in the 3d sublevel. But the outer shell here is the 4, so it really has 2 electrons in its outer shell. However, it can lose 2 electrons to make a 2+ ion, but it can also lose 3. It can lose these 2 electrons in the 4th, but also this 1 electron in the 3rd. There's not a lot of electronegativity on this scandium atom, and 1 electron is not too hard to lose. So it could lose 2 or it could lose 3. So in circumstances like this, you need to say which one it is. So if I lose 2 electrons, it would be scandium 2+, charge, and we would name that scandium Roman numeral 2. If we lose 3 electrons, if we lose those 2 in the valence shell and the 1 in the 3D, it now would be scandium with a 3 plus charge. It's not showing on my screen, but the way you would name this is it would be scandium Roman numeral 3. We'll talk more about these Roman numerals and when we use them later, but generally you need to use them when an ion can become more than, or an atom can become more than one kind of ion. And that tends to happen in the transition metal zone, the group B elements, but sometimes it doesn't. Let me show you an example. So here's silver. Its predicted configuration is this, but remember, anytime we have a situation where I have an almost filled D sublevel or a almost half filled D sublevel, I can take 1 electron from the S, and that's what's going to happen with silver. So silver has 1 electron in its valence shell, 5s1. Now we have the electrons in the D. It's not its outer shell. We saw before with scandium that we could take some out of that sublevel, but we can't take 10. So silver atom electron configuration would only be 1 electron in the outer shell, and if we lose that 1 electron, it becomes a silver with a 1 plus charge. We would just call it silver ion. There's no need to do Roman numerals because it can't be anything other than +1. Charges of more than 3 plus on a metal are rare. There's no way we're going to take 10 electrons out of that 4D sublevel. Okay, so let's look at anions. Nonmetals gain electrons to achieve a noble gas configuration. They can do so because they have that strong electronegativity that we were talking about in chapter 6. When they gain negative electrons, it makes them into negative ions, or an anion. One way that you can remember this is anion is a negative, N for negative, ion. So here's sulfur. Here's sulfur's electron configuration. Now if we look at its outer shell, which would be 3, it has 2 in the S and 4 in the P. Now that's not a filled outer shell or a complete octet. That would only be 6 in the outer shell. So I'm hoping you can guess how many electrons sulfur is going to gain to complete its octet. And of course it's 2. If we put 2 more electrons in that 3p sublevel, it will be 3p6. So we'd have a complete outer shell of 3s2, 3p6. So if you gain 2 negative electrons, no surprise, sulfur's charge would be 2 minus. So to do the electron dot diagram for an anion, you first need to recognize that it's a nonmetal. Generally, they're going to have a lot of valence electrons, 5 or more, and then they're going to gain the number of electrons that they need to fill their outer shell. So let's do phosphorus. Phosphorus has 5 valence electrons. So there are the 5 valence electrons, and I have free spaces here, here, and here to gain electrons, and that's exactly what's going to happen in phosphorus's case. When it gains those 3 electrons, what kind of charge is it going to have? 3 minus, of course. And the way you show that when you write the electron dot diagram for a nonmetal is you could write all the dots in 3 minus and that would be fine. But you might see these brackets that are around the elements. That's typically how you show an anion's electron dot diagram. And then you have to name it. So in a metal, all we had to do was write the word ion at the end of it. Now nonmetals are a little more complicated. In a nonmetal, you have to drop whatever ending the atom has. So phosphorus, the us part, gets dropped, and you add the suffix "ide." So phosphorus becomes phosphide ion. Oxygen becomes oxide. Fluorine becomes fluoride. You get the idea. And of course, you need to show all the dots for an anion because they're going to gain however many dots they need to have a complete octet, which is 8 in the outer shell. So you need to draw the element symbol, 8 dots, and give it the appropriate charge for however many dots it gained. So let's summarize what we've learned here in this video. Metals lose electrons when they become cations. They do this because of their weak pulling power in their nucleus. So they lose their dots, and you show no dots on the electron dot diagram of an ion for a metal. So they lose all their valence electrons, but they're going to gain a positive charge of however many electrons they lost. So however many electrons they started with it would be plus whatever that charge, whatever that number would be their final charge. Nonmetals gain electrons when they become anions, and that's because they have the strong polling power. They have a strong electronegativity. And they gain as many electrons as they need in order to fill up their outer shell and become stable. In doing so, they gain a negative charge of however many electrons they gain.